So now I have a relationship of T, and I also have a relationship between X. So do you remember when we started, we wrote this? So we needed a relationship between X and T. Now, bringing us back to a laser light, keep those things in mind. Then for a laser light, the cavity must have, number one, two highly reflecting surfaces, which in case of light would be mirrors, two highly reflecting mirrors surrounding the gain medium. Number two, standing waves with conditions that nodes must occur at the mirrors. So what if the nodes don't occur at the mirrors? What will happen? What will happen to the reflection? It'll be highly damped. It'll just go away. So those are the two conditions that we must have for standing waves when we talk about laser lights, which are not necessarily just limited to laser lights. Any standing waves will have the same condition. So the length of your cavity, going back to this picture, may I replace this picture with mirrors on both sides? Because now I'm talking about lasers. May I call this M1 and M2 mirror? So then what must be my condition for the length of how far these mirrors can be? Let's call it B. Implies length of cavity D must equal m lambda over 2, where m was our integer, right? That represents the modes. How many node to node points can fit into our cavity? That's called m, where m is an integer. So for example, in the one I've drawn, how many nodes do you see? So how many waves can you fit in there? 1, 2, 3, 4. So what is m? 4. Oh, let's look at it. So there'll be 1, 2, 3, 4. Now, similarly, I can also, knowing the stuff I know from before, I can find the frequency of the standing wave. What do I know about speed? C equals lambda f, or f equals c over lambda. I can find the value of lambda from here and plug it into here, which would be f equals c over 2d over m, or f equals mc over 2d.